Right. So as usual, start with updates. Anybody have updates to share? Papers published, students graduated, defended, cool projects started, anything like that?
Tell us about your Thursday, or no, Wednesday.
Wednesday evening.
At Bang Brewing.
Oh, yeah, that was interesting. So Wednesday, I was invited to a happy hour at Bang by some students in the Carlson School. They are part of a thing called the Funds Enterprise, which is kind of between a club and a class, where they actually have some investment funds that they manage. And one of the companies they invest in is, I always forget, it's like PMGI or something like that. It's a big ingredient maker, and they serve the distilling industry a lot and other food industries. So they, as investors, have some leverage over the company, and thought it would be interesting to pitch that the company work with Kernza. So I talked with them during their project, and they wanted to, there's really only a couple students working on the project, but they did this happy hour for about 10 or so students, and their leaders at Bang. So we got together, and Sophia Skelly was there from the Land Institute too. So we did a couple of little spiels. They asked us some questions and just broadened the understanding of Kernza across that group, which was pretty interesting. And then I ran into Jim and Yoakum there as well.
Just happened to go there. The place was packed. There's like no place to sit.
Yep.
Because Mitch was there.
And
Yeah.
Bang is the brewery that has Kernza beers already, right?
Yes, exactly. So we were all enjoying Kernza beers and talking about Kernza, and it was great.
It's cool.
Mhm. Policy update. That's the main thing I want to give as an update before we really dive in. So we have two bills that are moving in the state legislature. One of them is to fund our research efforts, and one of them is to fund the Value Chain Development Fund that is just being launched right now by the Department of Agriculture. That's brand new. There's a third separate piece of legislation that is going to kind of move independently, and that's what will hopefully, fingers crossed, deliver the Clean Water Fund research dollars that we have gotten every biennium for a while now. So that's moving on its own. These are two separate bills. The first one, like I said, is for our research. It would provide some base funding and allow us to stabilize soft funded positions and meet other major needs that we have, hopefully going forward into the future. Once it's passed, that money would come in every year unless the legislature in its wisdom decides to do something different. So they can always change their mind, but we would have a lot more stability a lot farther into the future than we do now, which would be awesome. The other part of that bill would be $10 million one-time funding for infrastructure and equipment. There's probably 3, 4, 5 times that much need for all the projects that we have and all the facilities and locations and everything to advance our work, but it would be an awesome down payment on getting people the equipment they need to conduct research. So that's bill number 1. And then bill number 2, like I said, is for the Value Chain Development Grant Fund. That would be targeting businesses like Perennial Pantry, like Perennial Promise Growers Cooperative, the Elderberry Co-op, emerging hazelnut businesses or that sort of thing that are based in Minnesota and that are part of the value chain for our crops. So smallish grants to those companies to continue developing those value chains.
Or a company that wants to put in a distiller.
Sure.
To deal with the meal from pennycress and camelina, as the example.
That would be administered by MDA grant program.
Mhm. So
That already exists, right?
the first round exists. They have about $500,000, and that's the applications will launch next month, I understand. But yeah, $500,000, it's pretty small pilot. So this would provide additional funds and let them continue that over multiple years. Any questions on those two bills? And we have Jeff Berg on the line too, who can tell us more if you want to, Jeff.
Yeah, thank you. I was going to give you an update on kind of the Clean Water Fund. So the governor has recommended $6 million for Forever Green would flow through MDA, much like it's happened in the last few biennium. That matches the Clean Water Council recommendation of $6 million. Like the bills Mitch mentioned, they haven't been jacketed yet, which means they haven't officially been introduced. So any of these, they're coming though, so that's good news. I'll put in the chat here for you can read at your leisure. So the Clean Water Council just came up with their biennial report, and you can find in there where it talked about Forever Green. So something for you guys kind of look at to see how you fit in the broader Clean Water Fund rule. And why I have the floor, the second thing I want to note is, thanks to Don, he sent me the whole bunch of a research report that you guys do for the last 2 biennium. I have finished reading them all. I thank you all very much for the hard work you do. Though a lot of times I have to Google different terms you use, I do appreciate all the work that you do and do all the heavy lifting. That is well appreciated by the state of Minnesota, including the one that's gonna be presented here today. So, I didn't know that, the bugs that go into fermentation, you could tell me I'm not technical on this, but I didn't realize the bugs that go into fermentation, do impact, fermentation and, kind of the products that come out of that. So thank you very much for the research that you do.
And we appreciate everything you do in support of the program and putting the time in to do quality evaluations of the reports that I send you. So.
Absolutely. Anyone else wondering about these bills or what else is going on at the legislature?
Well, I also remind you that folks from this group and outside and your associates will be asked to testify. So some of you, as we indicated before, will be called upon to ask you if you are willing to testify.
Yeah.
So we're trying to put a real mix of folks associated with the program in front of them. They love young people. They don't like old faces. What I'm saying is they really enjoy having students and farmers and the folks that are really being funded and getting benefit from the program there to make presentations to them.
Is there anything in person this session, or do they still have some Zoom activities?
Zoom is allowed in the Senate at least, and depending on the committee room that you're in. So that's great because we might have some folks testifying from outstate or other states even. That makes it easier to testify for us, but the meetings will be in person. It's just there's an option for people.
Is that also true in the House?
In the House, I think it depends more on which room you're in, is what I was told. So if the House hearings are held at the Capitol building, then they have the technology, but not every House hearing room has it, something like that. So. Yeah, and I put some feelers out to, get lists of folks within the community who want to testify or even just attend. So we have a hearing next Wednesday afternoon. So we're pretty good on testifiers, but if you want to attend, let me know. And I'm going to try to organize carpools from campus to get people over there just to, it's interesting, learn a lot, and it's good to show support.
Yeah, that's right. And having people in the audience when I may present the overview that we can refer to people that are in the audience, I think is also helpful.
Hey, Mitch, Peter here. Would you mind circulating to this group the letters of support? I bet that a bunch of the FBI affiliated folks here work with organizations that would be useful to sign on.
Sure. Yeah, I can get those out just to the Forever Green list. Good idea. So the other thought is, we're also always looking for partners, whether they work in clean water, they are farmers, they have a business related to these crops. We've got a pretty good list of folks like that who we can call on to testify. But if you all, with the projects you're doing, think of others, new people you've met, they have a project with, that sort of thing, just send them my way and we'll get them into the mix, because it always helps to have more options that we can call on. So with that, I think we'll turn it over to Bo. So we're all excited to learn about fermentation of pennycress and camelina, and the work that you've been doing. So take it away, Bo.
Thank you, Mitch. Thank you for having our group here. So today, I'm going to talk about the fermentation of pennycress and the camelina meal to improve their feeding quality. As we know that the U.S. agriculture is has been entering into the golden age in recent decade, when we have a huge bioenergy industry set up in the country. So a large amount of agricultural products have been converted to different type of biofuel products. And then this caused a massive scale of industrialized agriculture and also a very intensive livestock industry. Somehow, this also have some negative impact to our environment. So as we all know that this is what we call the nutrient pollution. We apply massive scale of fertilizers and as well as large amount of manures and to our environment, and all these unused nutrients somehow leach to our waterway and eventually cause some eutrophication. So that's a mission of my research group. Over the past decade, my group has been working on different aspects of this nutrient pollution to try to minimize the environmental impact of this biofuel industry in this region. So we set up a microalgae fungal leaching platform and used this platform for different applications. We also got funded to develop different type of wastewater treatment technology to remove nutrients, recover nutrients, as well as reduce the sludge volume. Recently, we started a new direction to work on the plant removal of different type of pollutants. And today we're going to talk about our efforts on the industrial fermentation for value-added bioproduct generation. So specifically, I'm going to talk about the food and the feed fermentation. I will briefly introduce two projects we currently we are working with. One is corn ethanol co-products generation. Another one is our new project with cattle feed production. And we finished one project for the fungal fermentation with canola meal because this is very similar to our forever green project. So I bring some slides to this presentation also. And then my student Christine and our postdoc researcher Xiao are going to introduce our research progress on the pennycress and the camelina meal fermentation. We also have Professor Chi Chen from a food science department joining us over Zoom. He will be our future collaborator to look at metabolites analysis and the food safety analysis for this fermented meal. And he will be joining us to answer any questions we may have. So as we all know, food fermentation is very common. It has been, we have these technologies ever since we have a human civilization. So it has multiple benefits. First of all, it improves the nutritional quality of the food components. And a lot of cases, it serves the preservation methods to have a longer shelf life for food components. Recent scientific research show that fermented food have a lot of health benefits, including increased diversity of our gut microbial community. In general, food fermentation will improve the digestibility of the food component. And it will also detoxify some of the raw material, some of the components like anti-nutrients or microtoxins. And many of us love fermented food because it improves the flavor, gives a different type of variety. And for the feed specifically, it will improve the palatability of the feed component. we commonly use all kinds of microbes to do the food or feed fermentation. This includes like the bacteria. Mostly we use lactic acid bacteria, baker's yeast, and some of the filamentous bacteria mold. So very common products we can think about the fermented food feed, like yogurt or the fermented milk. So most cases we are using lactic acid bacteria to convert the lactose so that people with lactose intolerance can enjoy this milk product. Kimchi or pickled vegetables, mostly we're still using the lactic acid bacteria to give us to help preserve the food and give us a flavor. Cheese, mostly it's lactic acid bacteria. Some cheese they use fungi. So like blue cheese, we're using penicillin to give the cheese a very special flavor color. Soy sauce is mostly fungi. Our Chinese people mostly drink the green tea, but the people in the Western world, they're mostly drinking the red or black tea. These are the bacteria fermented teas. We're using the baker's yeast to prepare our bread. And in the feed world, silage, we mostly don't think silage as a fermented feed, but it's actually the lactic acid bacteria fermented feed material. So it will increase flavor and also have the longer shelf life. Fermented soybean meal is market product, so it's a much higher value feed material, so specifically targeting on the young willing pigs, so they will have a better digestion on the soybean meals. The first project I want to introduce here is our corn ethanol co-products fermentation project. So this is funded by the National Science Foundation. We have been working for over 4 years. So the primary purpose for this project is to deal with food, environment, food, energy, and water nexus stress. If you look at the corn ethanol production process, it is a very energy intensive process. And because we have to involve a lot of energy to dry the co-products and eventually serve as animal feed. And it also, when they serve as the animal feed, so the whole process here is we convert all the starch material in the corn to ethanol, and then this is what we use as a biofuel. And then all the rest materials, we dry it and to serve as animal feed. So this drying process is a very energy intensive. And when the DDGS, the co-products, when we use it as animal feed, it's not a very properly, very well digested by the monogastric animals. Therefore, it causes a lot of value loss on the phosphorus and nitrogen, and eventually also cause some environmental issues when down the road. So what our approach here is we use a different type of other low quality agricultural feed mixed together with a whole silage, and then use bacteria and algae from bacterial fungal fermentation to improve the feed quality. So we just finished this project, and we already published around 10 papers on this topic. Developed a different type of fermentation strategies to improve the feed quality. So we found that it can increase key amino acids, key essential amino acids. It will degrade the phytate, and it will also degrade the microtoxins we see in corn ethanol co-products. So a lot of stuff, we're going to see this in our pennycress and camelina meal fermentation also. We recently started our new project. So this time we will try to apply this feed fermentation concept into the cattle feed. This project is currently funded by the USDA, and then we are collaborating with dairy group at the University of Pennsylvania. So the idea here is we are using different type of food waste to work on a fungal fermentation to remove mycotoxins as well as lignans. So hopefully we can improve the palatability also. And then with this fermented fungal fermented food waste, we're going to combine with other material to do the ensilage. And eventually we want to develop this novel feed that will address the overall environmental sustainability, as well as provide a more abundant nutritious feed to the cattle. So we just started this research, and we had our first paper recently published. The third project I'm going to talk about here is a fungal fermentation to improve the nutritional value for canola meal. So this project we already finished 2 years ago. It was my student Fatima. She did her PhD dissertation on this research, and it was a joint research program and funded by the Norwegian Research Council. So I want to spend a little bit more slides on this project because canola meal shares a lot of similarities with our pennycress and camelina meal. So canola is the second largest oil crop around the world. It's around a quarter. It's a little bit over a quarter of the oil consumption, just after the soybean meal. And the canola meal has very similar processing methods as our pennycress and camelina. So basically, we go through either the cold press or combined with soil extraction to remove the oil, and then the leftover will be the canola meal. When we mention canola, it is one type of rapeseed. So rapeseed is a more general, a broader category of the oilseed crop. But rapeseed has a very high concentration of uric acid, so it's not very healthy for the human consumption. And over several decades of research in Canada, they developed this double low or double zero rapeseed, and they name it as Canadian oilseeds low in acid. That's short for canola. So if you look at the canola meal, it's very abundant. It is the second most abundant plant protein source. It's very nutritious. It has a different type of vitamins. It has very balanced essential amino acid profile. However, it has certain issues. It is high in anti-nutritional factors such as glucosinate and synaptic acids. It also has lignocellulosic materials. Has a certain concentration of lignin, so that will literally prevent its wide application in monogastric animal and fish feed. So it contains high concentration of phytate, which the monogastric animals cannot use. Phosphorus is the third most expensive components in the animal feed. So if monogastric animals don't have phytates, they cannot utilize all the phosphorus source in the canola meal. So with fungal fermentation, we developed in our lab. Here's a summary what we find out. So if you look at the canola meal, the protein level is around 47.8%, and has a very high concentration, like a 14.22 nanomole per gram of glucosinate, 98.33 micromole per gram of synaptic acid and 2% of the phytate. So with fungal fermentation, we developed the fermented canola meal will have a very similar concentration of proteins, and it will remove almost all the most of the glucosinolate and the synaptic acids, and it reduces half. It degrades almost a little bit over 50% of the phytate, and overall it improved the digestibility when we did the in vitro digestibility study. So then, David brought our group into this Forever Green initiative, and we found that the pennycress and the camelina can also serve as oil seeds. The oil seeds meal probably will have a very similar feature as the canola meal. So I will hand the presentation to Christine, and she's going to talk about the camelina meal fermentation, and Xiao is going to talk about the pennycress meal fermentation. Christine.
Is that enough to pick me up, or should I?
Yes, you're right.
Okay. Hi, everyone. I'm Kristen, she, her pronouns. I'm a master's student in Bo's lab, and I've been working on solid state fermentation of camelina meal for improved monogastric animal feed.
Oops,
Oh.
sorry about that. Just trying to get your photo to show better and I messed everything up. Now we have just Bo's photo showing. There we go.
Okay.
I'll just leave it at that.
Great. So camelina, as you all probably know, is an oilseed crop that has a short growing season and can be grown over winter, so it doesn't interfere with corn and soybean rotations. It is well adapted to northern climates and has low fertilizer, pesticide, energy, and water requirements. And as a cover crop, it has an array of environmental benefits. It protects the soil from erosion, reduces nitrate and phosphorus leaching, and is a good food source for pollinators in the spring. However, despite its ease of growth and environmental benefits, it has a low adoption rate as a cover crop due to lack of economic returns. Camelina seeds have a high oil content between 30 to 49%, and this oil, as Bo mentioned earlier, can be extracted through a cold press or combination of cold press and solvent extraction. The oil has a variety of applications and can be used as edible oils, biodegradable plastics, biofuels, and more. And the meal is the byproduct of the oil extraction and what this talk will focus on. Although oil is the most valuable component of camelina, there still is great economic potential for the meal. This chart just kind of illustrates that although the price of canola and soybean oil is much higher than that of the meal, the greater percentage of meal versus oil means that soybean meal makes up around half of the revenue of soybeans, and canola meal around 20% of the revenue of canola. So similarly, the economic potential of camelina meal can be overlooked. Camelina meal has mid protein levels and fairly low fiber, making it suitable for animal feed. However, the presence of anti-nutritional factors, particularly glucosinolates and phytic acid, limits the inclusion of camelina meal in swine diets. This chart shows a comparison of soybean, canola, and camelina. Soybean is kind of the gold standard for swine feed. Canola is an emerging part of the market and is closely related to camelina. Soybean meal has the highest amounts of protein, lowest fiber, lowest lignin, lowest glucosinolates, and lowest phytate compared to the other two. Camelina and canola are quite similar in their composition, except camelina has higher glucosinolates. Glucosinolates are organic compounds derived from a glucose and amino acid. They're a diverse group of compounds with around 130 different glucosinolates being identified. And in camelina meal, there's 3 different glucosinolates. They're all aliphatic, which means they have a long carbon side chain. And glucocamelinin is the main one, which accounts for over half of the glucosinolates in camelina meal. These are all anti-nutritional factors. They can inhibit iodine uptake in the thyroid and also have negative effects on the liver and kidney. In swines, they're associated with lower fertility and lower growth rate, as well as higher levels of mortality. Swine tolerance is believed to be around 2 micromole per gram, and camelina meal glucosinolates range from 14 to 45 micromole per gram. This value is usually lower in winter camelina meal, but even at the lower end of this range, camelina can only be included in swine diets at around 10%.
So the swine tolerance, is that true just for camelina's glucosinolates, or that glucosinolates in general?
That's glucosinolates in general. And I think it's, you know, the effects of specifically camelina glucosinolates aren't super well known. Since they have a long carbon side chain, that's usually associated with less toxicity than the shorter side chains. So the number could be higher, but I don't think that it's super well studied. And then phytate is another anti-nutritional factor in camelina meal. It's non-digestible phosphorus. And not only is the phosphorus not available to be absorbed by the swine digestive tract, but it becomes negatively charged and can chelate with protein and other minerals, these also not bioavailable. And since the phosphorus isn't absorbed by the animal, it's excreted as a pollutant into the environment. And camelina levels are reported to be 25 to 32 grams per kilogram. And there isn't a standard for this in swine diets, but the lower the better. There's several strategies in place to address these anti-nutritional factors. Glucosinolates can be addressed by selective breeding. However, this takes time, and I know breeders have a lot of other goals for breeding, so this could help reduce breeding burdens by addressing the glucosinolates in another manner. And glucosinolates can also be reduced by steam stripping or solvent extraction, but this results in protein loss and an environmental pollution. Phytate can be addressed by including phytates in animal feed, but this has diminishing returns once 30 to 40% of the phytate is degraded. Our proposed solution to address these issues is solid state fermentation, which is microbes grown in an environment without free water. It's more cost effective and sustainable and has fewer energy and generates less waste than submerged state fermentation. And it's been previously shown to improve the nutrient profile of other similar oilseed meals. It's best suited for filamentous fungi, as these can naturally grow on complex natural substrates. And this could help reduce breeding burdens for camelina. Our goals are to convert camelina meal to an improved feed ingredient to increase its economic return and thereby increasing its adoption rate as a cover crop. We will do this by developing a bioprocessing strategy to increase the concentration of amino acids, decrease glucosinolates, and decrease phytic acid. This flow chart shows my research progress. The pink boxes are the steps I've completed so far. I've conducted several different fermentations as part of the screening process to identify the best fermentation candidates. And I'm going to talk about 2 of those fermentations today. And I screened 8 different bacterial and fungal species. Most of these are commonly used in the food industry, and the ones that aren't known to produce toxic metabolites. All of these have been previously cited in literature to have been used in solid state fermentation with similar effects that we're trying to achieve with camelina meal. And I'll be referring to these organisms by their abbreviated names for the rest of the talk. We obtained camelina seeds of the Joel variety, and these were cold pressed and then further defatted by hexane. And the microbes were cultured in liquid broth, and this was used to inoculate the substrate. For the first fermentation, I used camelina meal at a 65% moisture content, and half of the species had a 4-day incubation time and half had an 8-day, just based off of these species' previous use in solid state fermentation and how quickly they grow. And at the end of the fermentation, a mold-like growth could be observed on all of the filamentous fungi fermentations. This graph shows the weight loss of each fermentation compared to the control. The weight loss is due to the fungi metabolism components in the substrate, and it indicates how well they grew. But also you kind of want to balance their growth with how much weight loss happens, because this will reduce your amount of feed. I analyzed the total amino acid concentration on HPLC. Some species had amino acid enhancement, especially PO and SC at 10 to 15% of amino acid concentration compared to the control. And some species decreased the amino acid concentration because they were likely using the amino acids in camelina meal as part of their nitrogen source. And this was kind of interesting because MI and RO are previously known to be good protein enhancers in solid state fermentation, but this just kind of shows that this is really substrate specific. I took a look at phytate reduction, and I found that TV was the only organism that significantly decreased the phytate compared to the control. And this was also kind of interesting because other species are known to produce phytase, but they didn't do that here. So I wanted to take a look if that was just because the fermentation was too short for them to begin expressing secondary enzymes. I analyzed glucosinolates on the HPLC also. And for this, I only took a look at glucocamelinin, which is the main glucosinolate in camelina meal, because the other glucosinolates, the standards had a really high price, and there was no way to look at them without having the standard for the specific glucosinolate. And I saw that TV and AO had the greatest reduction in glucocamelinin at 81 and 76% compared to the control. I was able to validate this data by sending one non-fermented sample and one TV fermented sample to Dr. Chen's lab for LCMS analysis. And this can look at all glucosinolates without having the actual standard present. This validated our HPLC method, as glucocamelinin, which is the 2 bars in the middle, showed similar reduction between the fermented and non-fermented samples. And it was also kind of nice because the other 2 glucosinolates also showed similar percentages in reduction. So this just shows that our HPLC method can be a useful screening tool. And then for any finalized samples, we can get them validated on LCMS. I did a second fermentation with longer incubation times designed to target phytate degradation. I also decreased my moisture content a little bit to decrease clumping of camelina meal and give the microbes more surface area to grow on. I used a 14-day fermentation time and similar temperatures as the first fermentation. The weight loss, the trends in the weight loss were the same as the first fermentation, but they were all a bit higher as the microbes had longer times to grow. All samples reduced in amino acid except for SC, and this was expected as the microbes were allowed to grow longer than what would be optimal for protein enhancement. And I was surprised to see that I had the same data as previously, with the only reduction in phytate being in the TV fermented sample. The hypothesis for this is that the free phosphorus that exists in the camelina meal is more bioavailable to the microbes. So they're just using this phosphorus for their metabolism, and they don't have enough incentive to produce the phytase enzyme. So from my screening process, I concluded that the best amino acid enhancement was in SC fermentations at with a 15% amino acid enhancement. The TV was the only good phytate degradator, and glucosinolate reduction was observed in TV and AO fermented samples. So I concluded that TV is the best candidate to degrade anti-nutritional factors. And based on what is known about the microbe, it also is a known lignin, cellulose, and hemicellulose degrader. So I haven't looked into that yet, but it will have the added benefit of producing fiber and lignin in the meal as well. And SC is the best candidate for amino acid enhancement. And under these conditions, TV didn't improve the total protein content, but I want to look into this more by identifying ideal fermentation conditions, particularly the addition of a nitrogen source. Previous solid state fermentation data shows that adding a nitrogen source can increase the concentration of amino acids. So I did a little preliminary experiment, screening all species and doing the same fermentation process as I did earlier, but with the addition of urea and ammonium nitrate at 1% nitrogen. And although TV didn't result in significantly increased amino acid enhancement, there were some species, particularly AO, that had a 20% amino acid enhancement with the addition of urea. The amino acid enhancement with an addition of a nitrogen source is specific to the species and also towards the nitrogen source used. So it could be worthwhile to screen different cheap nitrogen sources to find one that would potentially work for TV to enhance the amino acids. So I concluded that AO could also be another good candidate to look into, as it effectively degrades glucosinolates and can also enhance amino acids with the addition of urea. And currently there's work underway to further optimize fermentation conditions. I am using software JMP design of experiments to simultaneously look at the effects of time, inoculation ratio, moisture, temperature of incubation, and nitrogen source on TV fermentations. And once I finish that, I'll complete that with yeast and potentially AO if there's time. And we'll take any questions.
As you go through this process, do we have the capacity within the institution to actually do the fermentation at a level that you could support feeding trials?
It's the
Yeah.
bag.
We have a cheap autoclavable bags
Yeah,
that could use 10 kilogram
yeah.
batch to
Yeah.
do the solid state fermentation.
So what would be the animal of choice for the feeding trials? Would you use mice? Is that where you would start first?
Yeah, mice will be the first trial. Then probably the monogastric animals like pigs.
Yeah,
Yeah, will be later.
yeah.
And also before that, we also have in vitro lab experiment.
Well, we do the in vitro test first. So this is simulating the digestion system with the in the outside environment, and then will give us some kind of screening tool to see what will be which cultivation condition will have a better digestibility, and then we choose I think that with the next phase, we're going to choose the mice at Dr. Chen's lab to look at the safety to see whether they are safe to feed the animals. And then next step will be animal trial. We can choose a variety of different animals like pigs or mink, sometimes even fish.
The other thing I would ask, and just to throw it out there, we can talk about it later, but when you go through this fermentation process, are you creating other compounds of interest? Like we have this new big facility coming here on campus, right? In terms of the fermentation process, pulling out of all of those compounds that we don't want, but is there also the possibility of creating through this process high value compounds that would move into the market. You see what I'm saying, in terms of pulling these compounds out, but having microbes that also use those compounds to produce a high value product, industrial product, for example, into the marketplace. I mean, we don't have to talk about that now, but in
Yeah.
terms of whether that is even part of the thought.
Yeah, I think that's definitely a possibility, and we just got a free program with Dr. Chen's lab, where they're gonna look at metabolites, so that would probably give greater insight to what exactly is being produced.
You know, to pull this compound out for the feed purpose, but also then creating another potential high value product for the market.
Yes. Christine, do you want to stop sharing your slides so that we can have a Xiao to finish up his? And then I think that some of the questions we probably can combine them together to answer. You know, I feel maybe like one type of question will be whether there are potential for higher value products. Another will be, you know, what about the processing or the cost, or how do we compatible with current processing facility, something like this. But maybe, you know, let's wait until Xiao finish his part on the pennycress, and then we probably can come back with all the questions.
Yeah, maybe I just make a quick comment with regarding Don's question about the potential appearance of additional chemicals from the fermentation. I mean, right now the analysis conducted in my lab is more focused on those the anti-nutrients, but then it does has this, as you asked the question, which is I think it's a good direction to move on to conduct what we call the chemometric analysis, which is looking at the global profile of the metabolites and the nutrient content of those fermentation products. And I think something should be done with regarding to that's the overall composition of the fermentation products, which we will have a better idea of those efforts.
Thanks.
So so hello everyone. My name is Xiao Song. I'm currently a researcher in the Dr. Hu's lab.
Speak up a little bit.
Oh yeah. I'll just check if I muted.
This should be picking up.
That will pick you up here.
It's actually better.
Okay, yeah. So my background is basically in the fermentation, all different types of fermentation. So in this project, I'm mainly working on the solid state fermentation for pennycress meal. As Christine just told, the camelina meal, pennycress meal is or pennycress is similar to the camelina, is called the cover crops, and it also produce oil seeds. And the pennycress is important because it can grow. It can be using as a cover crop in the rotation of the soybean, and also it produce it helps the soils to maintain the nutrients from being run off to the water bodies. So, and the pennycress also provide a lot of benefits, like it can use as pollinators for use the nutrients for the pollinators during the early spring. And we are mainly focused on the pennycress meal fermentation. And before that, I'd like to just briefly talk about the seed. So pennycress seed is about 20 to 36% of oil, and this oil can be basically used for the biodiesel production. And also it contains about 20 to 25% of crude protein, and about 22% of them are amino acids. It also contains some 17 to 20% of food fiber. Besides that, pennycress seeds contains some anti-nutritional factors like glucosinolates, synaptic acid, and phytate, as Christine just told about in the camelina seeds also. So in our project, we we actually have the integrated process. We're gonna use pennycress seeds, and we do the oil extraction. And meanwhile, when we use and also we use the cakes and the moisture from the processing of the seeds, and making them as a makes both cake and moisture as a good substrate for the fermentation process. And during the fermentation, we can use a different type of bacterial or fungal strains to reduce some of the anti-nutritional factors, and meanwhile improve some already nutritional factors like proteins, amino acids, and reduce of digestible indigestible fiber components. So make the pennycress meal more like nutritional for the monogastric animals. So this basically the pennycress meal. It has 4 issues. The first one is it has high concentration of lignin or non-starch polysaccharides, and the glucosinolates, fatty acids, are considered like anti-nutritional factors, not either not digestible by animals, or it's not good for the health of animals. And also the amino acids in the meal are not well balanced. Some key amino acids are even lower in the meal than the other protein-rich sources. So through the fermentation, we can basically we will be able to reduce the negative effects from the anti-nutritional factors, and also improve the nutritional factors, and like increase the metabolizable carbohydrates, like protein, amino acid, and also reduce the fatty acid and release the more like phosphorus and other available minerals. So here I just talk about the case study about what we have done in the lab using the solid state fermentation of pennycress meal. The strains we selected are PO, RO, AO, MI is short for the fungal strains, which already covered by the praise. And these 4 fungal strains are generally considered safe. So some fungal strains like the PO is called oyster mushroom actually. And AO is a fungal strain used for the soy sauce production. MI and RO used for the tempeh production in Indonesia. And we use the substrate. These are all the conditions we use, and first moisture content in the substrate. And we need to sterilize the meal to make it not affected by other germs or contamination by other bacteria. And the fermentation time 6 to 14 days. And we analyze the amino acids, phytate and free phosphorus, and the structured carbohydrates and soluble sugars. And also we analyze some mycotoxins that could be degraded by the fungal strains. And finally, we did the in vitro digestibility in the lab to see the digestibility of the dry matter and the amino acids. So the first one is that we put total and essential amino acids. So in this graph, left graph here, the control is the non-fermented meal, and PO, RO, AO, and MR are like 4 separated fermented meal. And we can see that the 4 essential amino acids like threonine, methionine, tryptophan, and lysine are the proportions to the total amino acids are increased. And also from the table, we see some of the essential amino acids improve, but other non-essential amino acids reduced. So that means actually in the fungal fermentation, the fungal strains utilize the non-essential amino acids in the meal and converted them into its own biomass, which is rich in the essential amino acids. That's good for the feeding mechanism. So, and also it can improve the balance of the amino acids. As we see the table on the left side, the soybean meal has a very well good balanced amino acids, these 3 key amino acids. But the pennycress meal has a little bit lower, especially the isoleucine in the middle. It's pretty lower. And well, after the fermentation, we can see that the isoleucine to the leucine ratio has actually improved pretty remarkably. So this means that fermentation also can improve the essential amino acid, the balance of these essential amino acids. And also the phytate and the free phosphorus So after fermentation, some of the fungal strains like RO, AO, and MI could reduce the phytate to a certain point, and also can release, once they reduce phytate or break down the phytate, it will release the free phosphorus to the meal, to make it more like phosphorus available for the animals. So, and this is a structured carbohydrate and soluble sugar. If you just go look at the soluble sugar, we have a cellulobiose in the fermented feed more than the control. And cellulobiose is component of cellulose. So the fungals actually break down the cellulose into the cellulobiose, which is more like available carbohydrates that can be used by the monogastric animals. And this is the mycotoxins. We selected three most critical mycotoxins: zearalenone, deoxyvalenol, is a vomitoxin, and also total-aflatoxins. And especially when we see that the zearalenone, the peel, which is oyster mushroom, when they fermenting the pennycress meal, it almost reduced, like completely removed almost all the zearalenone. And also, it has also ability to degrade vomitoxins and total aflatoxins. Other fungal strains have also trained, but not that very significant. And then we did like in vitro digestibility analysis. So in our lab, we use like a lab equipment to mimic or simulate the different steps of the pigs. So there's a total 3 steps. The first 2 steps is the pepsin hydrolysis and pancreatin hydrolysis to mimic the stomach and the small intestine to evaluate the digestibility of the protein and the dry matter. And the third step is simulating the column of the pig. So it's actually using the fecal inoculum to do the fermentation of the fermented feed to see if the fibers can be degraded. So in this study, we did only like the first 2 steps to see dry matter and the amino acid digestibility. So here is the bar chart in the left side is the in vitro dry matter digestibility. Although some of the fungal strains like PO, RO, MI does not have improved digestibility, but the AO have a little bit improvement of dry matter digestibility. And we see the table in the amino acid digestibility. We can see that the AO also have especially higher digestibility of essential amino acids like tryptophan and lysine, and these 2 amino acids are important in the swine nutrition. So we have a conclusion about this study that some fungal strains can convert non-essential amino acids into essential amino acids in the feed, and also it can could improve the balance of some key amino acids. And also it can break down the phytate to release the available phosphorus. And it can also break down the cellulose or fiber into the more digestible fiber components. And also some of them also like PO can have ability to degrading their mycotoxins. And the AO, which is very commonly used the fungal strain for soy sauce production, showed a higher in vitro dry matter digestibility and key digestibility of some key amino acids. So our future direction will be we will not only producing the feeding materials, but will expand more products. Like we use a fungal strain because fungal strains in the fermentation, they will produce enzymes. So enzymes would be one of our interest other products, industrial value products. And also for the pennycress meal, we can also evaluate their ability to their capacity to be used as human food supplies, like soy sauce that already are commercialized. And then in the future, once we have like the analysis, economic analysis, and we will think about the scale up of the process that could produce processing more like a meal to produce mass production our design products. So yeah, that's on my presentation.
So in your system, the pennycress, were you able to degrade the centigrade?
Centigrade.
Yeah.
Yeah, I think yes. We did some study.
I was just wondering, so in the case, it's a, different compound, right, between those two species.
Yes.
Were you able to degrade the glucosinolate in your system?
Yeah, but I didn't include the data. We
I
have
understand, just that's the reason.
Yeah.
You noticed I caught it, that was missing.
Yeah, yeah.
But you can take it down to damn near zero, right?
Yeah, you mean a centigrade, right?
Yeah.
Mhm.
Okay.
This is a rudimentary question, but how, for both of you, how common is it to combine, like, I remember, like, some have different benefits, like, you talked about TV and, like, do you combine those often, and like, is that a nightmare, or like, is that common to combine, do you get multiple benefits, or?
This is sort of an emerging market, so it's, just doing fermentation on animal feed isn't really a thing that's commonly done. We would probably do it in like a sequential fermentation
Not
instead
the
of
same,
at the same time, so they don't compete with each other. But it wouldn't be difficult to do.
Yes, so you're talking about the combine different formulas.
Yeah,
Yeah, that's
combining or doing it sequentially, like, could you get some of the benefits of each of those?
yeah, that's true. We actually, that's called a co-culture fermentation. We use a different fungal strain with different capacity to culture them together, and that would have some values combined degradation of some anti-nutrition factors, and also could induce some other compounds production. And we did those study in our previous project with corn DDGS, which proved that it works.
Yeah, I think in the screening, we still try to find an ideal candidate that can address most of the issues. No matter it's a sequential fermentation or co-culture, they bring the complexity to the whole system. So ideally, if it's a one strain doing all the work, that will be still a very ideal scenario. So that's why both Xiao and Christine, we try to screen as many strains as possible to see whether we can find the best strain that can address all of the issues here.
Isn't fermentation very commonly used in Europe and other areas of the world to modify products for food and feed?
I think it's widely used in everywhere, right? So like bread, we eat every day.
No, I don't mean that. I mean in terms of processing meal for feed. It was my understanding that it was pretty common in Europe. Is that true or not true?
So it is a common in, maybe I can bring we can bring Pedro and Jerry next time with our conversation, but it's more common than here. Fermented feed is relatively a new concept for the US market, but we see several products already, like fermented soybean.
Well, I'm excited about this work and the possibilities, but I'm also very interested in having an approach that just doesn't make it feedable, but also creating a product that has high value, that's different than what you're currently getting out of some of these other meals, and producing a new set of products. In other words, ramping it up to, so it isn't just bad, that it's really good and it has components that have great value in the food and feed system. And I'm sure you guys are thinking of the same things.
Yes. So one like fermented soybean meal, even though it's a small step to improve the quality of the soybean meal because it has a niche market. So the target is this winning pigs. Their price is literally double the current price for soybean meal. So that's one way to look at this one. At least you double.
What is that niche market for soy?
So
Weaning-
weaning pigs, there's young pigs, when they just quit their mother's milk, they still have a relatively weak digestion system. So people feed the fermented soybean meal that will be better for them to digest. And the fermented soybean meal is sold as at least $800 per ton. So it's almost twice the price as a regular soybean meal.
Yeah.
I'm curious about the scaling of this on an industrial level. So if it's being done for soybean meal with weaning pigs, it's got to be fairly large, but are we talking about, large stainless steel bioreactors? Can this be done in a pack type setting, like, pack silage? How much infrastructure and equipment is needed to bring this to a real industrial scale?
So yeah, I think one of the Frank is also asking this question in the chat box. So in terms of how this process, how much additional cost it will bring to the feed and what additional processing equipment that we may need to have. So I think this is a really good question that we can continue to explore. Feeder fermentation, solid state fermentation is more suitable for small scale operation. In the liquid fermentation is more suitable for large scale operation, so that we have a huge fermentation tank. How we eventually implement this one to the field, this is something we will continue to explore on different options. Xiao recently bought this fermentation bag. So it's an air permeable bag. It can be scaled at a much larger scale, it can be scaled up to a much larger volume. And we also think about this agriculture bag, ag bag, that can be one of the ways to do this type of fermentation. So we'll see how this will eventually evolve. Currently, what I can say here is it will not interfere with your current refining or processing facility, because if you look at the Xiao's proposed process flow chart for the pennycress meal processing, we are just using the moisture from the cooking and then the meal to set up additional facility for this fermentation, so it will not interfere with the current cold press or the soil extraction process. But in terms of the overall economic analysis, this is something when we finish up this project, we will pretty much have a good idea on how much profitability we're looking at.
Did you see Jeff's question?
Let me see. Yeah, David asked me a question here. Let's say in terms of phytate reduction, how do the reductions in fermentation compare to reduction achieved by just treating the meal with the phytates? That's a good question, David. So basically the idea is very similar. So even the industrial phytate, this is like a #1 industrial enzyme, it is still produced with fungal fermentation. So the difference here is that now you have an industrial enzyme you're adding to the feed, so you hope that phytates will degrade the phytate.
The reason I brought that up was simply it looked like for the phytate business that you only really had one good fermenter that was taking it out. And so it might, if you just, if the other ones are better and doing a better job, it might be cheaper just to add phytates and then go with the other guys.
Yes, I think I see your angle. First of all, adding the phytates to the animal feed is not 100% degradation. So we can read a different type of reports. They say somewhere like a range of 50% to 70% of the phytate can be degraded when adding phytates to the feed. So, you're looking at a process to produce a phytate, and then you add into the feed. But here, if you have the fungal fermentation, this will be the additional added benefits because we want to increase the protein content. We want to balance the amino acids. We want to reduce glucosinate. By the way, it can also reduce a phytate. So this is the additional benefit to this one. So I think the goal is not mainly on the phytate degradation, but it's additional benefits. What I feel, in the future, if this fermented feed as one of the components to formulate with the corn and soybeans to eventually become an animal feed, they still need to add industrial phytates there because the corn will produce probably still have phytate. Soybean meal still have a phytate, other components. So they probably will add less. The required phytates addition probably less because we have this fermented oilseed meal here. This part of the phytate, at least we don't need to worry about. Does it make sense?
Yeah, well, that makes sense. I have a question too, just a kind of a broader thing. If Matthew Oda's still on board, I know he did a study with Nick Jordan on looking at Lake Pippin and phosphate. And I was wondering if that phosphate was coming from phytase. Matthew, are you on?
Yes, I'm on. And I'd say that area with Lake Pepin is more of an issue of geology than I guess waste. Just there, that's that southeast region of Minnesota has got the terrain with a lot of hills and it's a lot of erosion. But anyway, it still doesn't mean that all this livestock manure isn't an issue for other places.
But the phosphorus that's going into Lake Pepin actually comes from bank erosion in the Minnesota River.
Right.
So that's the flow of phosphorus into Lake Pepin.
Yes, exactly.
Okay, thanks for that clarification.
Just wanted to follow up on this before we get to Jeff's question too. So it looked like the results were a little bit more promising on pennycress for phytate reduction than camelina. Do you have, maybe I misread it, but if that's right, do you have any hypotheses as to why that would be?
Yeah, we are trying to understand why this happens. I think Christine's committee member also give us some suggestions to figure out why pennycress is more effective in removing the phytate. So one of the hypotheses here is, as Christine mentioned, camelina probably already has a very high concentration of free phosphate available in the meal. That's why if we have a lot of free phosphate available in the meal for the fungal to use, they probably won't be able to generate a lot of phytates, the enzyme to degrade the phytate in the first place. So that was one of the hypotheses. TV, this strain is very unique because TV is a strain that is least affected by the substrate. So this is a super good degrader. They degrade the lignin, cellulose, hemicellulose. They degrade everything without considering all these nutrient limitations to raw material. So this is why we see this strain reduce phytate really well, even though we have a hypothesis that camelina is very enriched with free phosphate. So that's our thought. We're not sure 100% yet.
Interesting, thanks.
So I think Jeff's question here is, let me see. So animal agriculture is Minnesota's largest source of methane emission, especially from manure management and cattle digestion. Could this research develop a product that address antric fermentation? What might this be? What is
Enteric fermentation that occurs in a cow's gut, in a cow's digestive system.
Okay. So you're talking about addressing the methane emission from the feed perspective, right?
Yes.
That's possible. So that's possible in terms of bacterial fermentation. So one way to address the methane emission from the cattle system is we add a rumensin in the animal feed, so that literally like suppress the methanogens and also promote the propionic acid production. So if you look at the overall anaerobic degradation, the more lactic acid or the propionic acid, carbon-3 acids being produced, it's really hard to convert all these carbon-3 acids into acetic acid, which is a precursor for the methane generation. So if we want to, I think this is a really good suggestion. If we want to move to address this methane generation from the feed point of view. So if we can convert most of the easy sugars into propionic acid or the lactic acid, it will suppress the methanogens in the gut system. But currently, when people add the rumensin in there, that's what they do. They suppress the methanogens by promoting the propionic acid production in the gut system.
Oh, is that the same mechanism as these kind of soybean, or not soybean, seaweed or algae-based additives that are also being discussed as a way to cut methane production from enteric fermentation? Or is it a different parallel approach?
I don't know in details about that mechanism. So if they supplement algae or seaweed into the cattle feed, I'm not sure whether so maybe the fermentation pathway will change, or maybe I don't know the details about that mechanism.
Well, regardless, if there's a way to address this issue with feed fermentation, that feels like a high priority to me. Could have a huge impact.
Yeah, that's a good suggestion. I never thought about this direction. Thank you, Jeff. This is something we can probably think about in the feed fermentation direction. So if we want to address methane emission, we probably can think about how to incorporate more like a propionic acid production bacteria into
that would dramatically increase the value of that meal. And that's exactly what I'm putting out there, right? That this is an example of a big step that could have a huge impact and really add value to this fermentation idea, right? So for me, just making it okay to feed, that's fine. But if you can take the big steps up like Jeff is suggesting, that is something for me that would be really, really exciting and big global impact.
Yeah, but the propionic acid doesn't smell really well, so I'm not sure whether people will like this kind of feed.
Very good. Any other comments, questions online or in the room? If not, we appreciate all the work that you're doing on these issues to advance the forever green crops, and look forward to working with all of you in the future, and hope that we can make some big steps after we make the little steps. So that's why I think we're all really excited about this new fermentation possibility. The other thing I will ask before you go, are you guys tied in? Is your lab though tied into this new fermentation facility? Are you part of that game?
Yeah, we are trying to see whether we can get some, I think that my whole department is trying to get some space in this biomanufacturing building. So, I think we have a couple of
factories. We've been searching for people that have real ties there to bring some of these ideas that we're talking about here into play. So if you get in, let us hang on to your and bring some of these ideas, like Jeff is saying, into that process. So
I see Tim Omasov just raised his hand. Do you want to jump in, Tim?
Yeah, can you guys hear me?
Yes.
Yep.
yes.
Well, I want to sort of thank Bo for the presentation. I enjoyed it immensely. Great job, Bo. I wish I had an opportunity to continue the collaboration that we were thinking about starting. Just for my education, just curious, you know, I had a boss at Monsanto, Tom Adams, and he is a fungal geneticist by training. And what I learned from him is that the fungi like to process their food outside, meaning they secrete all kind of hydrolytic enzymes, including proteases. But the outcome of your fermentation is high protein meal still. I'm curious, were these strains selected to be deficient in certain proteases, or why they actually don't chew up most of the protein?
So fungi, they're going to produce hydrolytic enzymes like lipase, cellulase. You know, this enzyme to break down the substrate, so they can utilize this substrate. So I think that's what I think that's probably what your friend is referring here. For our fungal fermentation here, so if we look at our raw material, the raw material has a very high concentration of protein in the first place, but it also has you know, lignocellulose materials, anti-nutritional factors. So really what we are utilizing fungi to do here is try to break down these lignocellulose structures, utilize all these resources to grow their fungal biomass. So we are not really expecting the fungi to utilize the proteins in the meal in the first place. So they may use some of the proteins in the meal to enrich their fungal biomass, but that's not our purpose. So most cases, proteins in the meal will remain. We hope the fungi will use other components of the meal. So that's our my explanation. You know, it's a little bit different from lactic acid bacteria fermentation in terms of protein digestibility. For the lactic acid bacteria, they somehow dissolve the insoluble protein into small polypeptides. So that in that case, the digestibility will increase. So this is what we see in the yogurt fermentation. The hard digestible proteins will be more easy to be absorbed by human. But the fungi, we are hoping that they can tackle these lignans. They can get rid of those hemicellulose, phytate, you know, these structures. So did I answer your question?
Yeah, I think mostly it did. I just encourage you to continue to look into that. Through engineering these microbes, you can achieve even greater things like producing these high value products that would be complementing the meal. Yeah, that's a perfect idea. Great job. Thank you.
Thank you.
All right. Any more questions? Let's thank Bo and Kristen and Xiao. Great presentation. Yeah. All right,
Thank you
take
all.
care.
See you next week, everybody.
Yep.